All right, so now that we're back in Houdini, let's go ahead and get this all set up here. So I'm actually going to come up to this delete SOP over here. And this is kind of my leftover polygons. These are the polygons that I'm not really processing anywhere else. They're just getting kind of fed back in as whole polygons. So these are kind of the perfect ones to process. So again, we're going to throw in another delete SOP, but we're going to split these out again into a couple different streams. So we're just going to use this noise expression. I'm going to copy this. I'm going to bring it down here to this delete SOP. We're going to say delete by expression, and we're just going to paste that right in there. And we're going to change this value to say, like, I don't know, 0.15. Let's try that. What I'm looking for is interesting islands. And by islands, I mean like this chunk here would be an island. And anything that still has like a corner connection here, that's not going to be an island. So like this little group is going to be processed all together. So I do want to delete a few more. Let's try like 0.17. Okay, so now I have a little bit more unique islands. Like this group of 3 is an island, this group of 2 is an island. This here is pretty cool little island. Yeah, that's great. Okay, let's go with that. So what we need to do is now we need to tell Houdini that we want to make sure that all of these polygons are in fact connected together and not separated out. So to do that, we're going to use a fuse SOP. Fuse SOP is very similar to the optimization function in Cinema 4D, where it just goes through and makes sure that if points are occupying the same space, that it's not 2 points, it's a single point, and everything is kind of fused together. Great. Now we need to tell Houdini that each of these little individual islands that we've got should be treated as a separate object or a separate component in our for loop. So we can do that in a few different ways, but the easiest way is to just use the assemble SOP again. So the assemble SOP again does, tons of different things, but in this case, we are using it to create a name attribute. And if we look at our polygon data here, and go over here, we can see we have our name attribute. So we've got, it starts with name. Piece 0 there's just one. It's probably one of these little islands that has just a single polygon. But then piece 1 is an island of 3. So like something like this, or one of these other islands of 3. And we can go all the way down to piece 55 at the very bottom that has 4. So we have, it looks like maybe 56 total individual islands. And you can see that if I middle click on my assemble SOP, I've got my name attribute, and we have 56 unique name attributes. Cool. So let's talk a little bit about what the subdivision function does. Before we get into any for loops or anything like that, let's talk about the subdivision function. Let's throw in a subdivide SOP and see what's going on here. We'll just wire this up. So we're going to look at this, and you can see what it does is it does indeed subdivide the polygons. So we had these, and now we have twice as many polygons, but it also does something very similar to the subdivision in Cinema 4D, where it kind of creates this sort of interpolated curve, like it tries to smooth the polygons out a little bit. And you can see as I increase this depth value, that curve gets a little nicer, but we don't really want the curve. We want everything to be nice and square, especially since it creates like really nasty things here along the edges and everything. This is not really what we want. So before the subdivide, I want to do some things. So we're going to do this assemble. In here in the middle is where we're going to put our for loop, and then we're going to do those things. But then after the for loop and before the subdivide, I want to drop in a facet SOP. And what the facet SOP is going to essentially do is take these fused polygons that created all these islands, and if I tell it to create unique points, it's going to split those out so each of these polygons are now their own individual islands. So now if I go back to subdivide, I no longer have that nasty curve. If I turn this off, I have crazy curves because each of these is being treated as a group of polygons. And if I tell it to be unique points, now we've lost the those kind of nasty curves that we don't want anymore. Okay, so let's talk about the for loop, the for each loop, and what that's going to do for us. So if I type in for, we actually have several different for each loops in here. And just like the wrangles, they're basically the same thing with some different settings. What we want is for each named primitive. And we're going to drop that in here. And you can see that's given us something very different from what we've seen so far. We actually have two nodes, and we've got this kind of bounding box thing that's happening here. And I'll explain that here in just a minute. So we're going to take the output of our assemble SOP. We're going to plug that right into this for each begin one node. And anything that's inside this bounding box, basically anything that goes between these two nodes, the for each begin and the for each end, is going to be processed in the loop. If I put my visibility flag down here on the for each end node, you can see it's saying gather 56. That means it's running this for loop 56 total times. Let's look at what these nodes actually have. So the for each begin one node is a pretty limited one. There's not a ton here. It's telling us what our method is. And in this case, we want piece or points. We don't really want any of this other stuff. We'll come back to this one, but this isn't, there's not a whole lot going on here. It's just telling it, this block path is telling it which for each end to actually process. The for each end SOP has a bit more going on. So we have iteration methods. So is it pieces or points, or is it by count? Like you can limit the number of times the loop runs. If you have a fixed number of times you want it to run, you can do that. We're merging the iterations. We're running over primitives. This piece attribute called name, that's what's being created up here on the assemble SOP. The assemble SOP is creating our name attribute. That's what all these are. And so what the for each loop is going to do is it's looking for differences in this name attribute, and it's processing whatever we put in here on the polygons that have the same name attribute. So piece 0 will be processed as an individual unit, and then anything that has piece 1 will be processed as an individual unit. Anything that has piece 2 processed individually, etc., all the way down to, in this case, piece 55, which is our very end. So this little for each loop here is actually really, really cool, because the alternative to that would be to do some really nasty things like throwing in like an attribute wrangle, wiring this up to our assemble SOP. Because we want to run an operation on each of these little islands, we would have to do something like, say, if s name isn't equal to piece 0, remove prim coming from input 0 at prim num, remove the points. You know, so there's what we would do to process piece 0. The next one we would have to do, we'd process piece 1, right? And then we'd have to split a stream that's processing piece 2 and piece 3, etc. And we have 55 of these things. Imagine if we had 5,500 or 55,000 of these things. It would just be impossible for us to go through and create individual data streams that process each of those pieces individually. It would be terrible. But that's essentially what the for each loop is going to do for us. It's going to allow us to run whatever is in here on each of those little islands all at the same time. So every single time step, it's going to run whatever is in this for each loop on all of those individual islands. Really, really cool. What I'm going to do is drop in an attribute wrangle, and we're going to throw this in here, and you can see that kind of gets grouped in with our for each node in this little bounding box, which is pretty cool. So we're going to tell this to run over primitives. And what I'd like to do is generate a different value on the primitives for each iteration that's being processed. Each loop of our for each loop, I want to have a different number on those polygons. And in order to do that, I need to know what loop I'm on while I'm on it. Luckily, Houdini has a really handy tool for that. We come up here to our for each begin node, and I click on create meta import node. You can see it's created a whole separate node that is disconnected from the rest of these things, that all it does is generate information about the for loop. And you can see this is on the detail attribute here. It's got 3 pieces of really important information. It's got the iteration. So as the loop is being processed, this number is increasing as it loops. So loop 0 is iteration 0, loop 10 is iteration 10, etc. It's got the total number of iterations. So that's going to be this number down here. And then it's got the name attribute for whatever iteration is currently being processed. Now, it should be said that because this loop essentially runs instantaneously, you are not going to see these numbers change here in the geometry spreadsheet. Whatever these numbers are basically represents the final value of whatever is being processed in here, but during the calculation, these numbers and values actually change. So what I need to do is get the iteration detail attribute from here into my attribute wrangle. So what I'm going to do is take the output of this. I'm going to plug it into input number 1, because again, we start at input 0. So this is input number 1 in my attribute wrangle. And I'm just going to create a really simple integer attribute to illustrate the idea that we are pulling the iteration number off of this node and creating an attribute for it. So we're going to create an attribute I at, let's call it iternum, and we're going to set that equal to a detail attribute. So we need to pull the detail attribute here. So we use a detail function. We are looking at stream number 1. So again, stream 0 is here, stream 1 is here. So we need to pull data off of stream 1, and it needs to know what the attribute name is. In this case, it's iteration in quotation marks. And then we need to close our parentheses, and we need to put a semicolon. Okay, so now if I go down here to my for each and I go back to polygon attributes, primitive attributes, you can see I've got this iternum attribute here. And I'm just going to push these noises off to the side. I don't really need those right now. But you can see piece 0 was a piece it's like one of these little standalone single polygons. It has iteration number 0. These 4, piece 1, 2, these 4, I'm sorry, these 3 here, these 3 all have the piece 1 name attribute, and they all have an iteration value or an iternum of 1. So you can see they're all being processed together. Likewise, these 4 polygons all have piece 2 as their name attribute, and they have an iternum of 2. So they were all being processed together on the second iteration, all the way down to the very, very bottom, where these 4 polygons that have piece 55 as their name attribute all have the same iternum value of 55. So what that's showing us is that not only is our for loop actually working, but it's showing us that each of those polygons that are in those little islands are all being processed at the same time through this attribute wrangle, which is exactly what we want. But I don't really want the iteration number. I want a random number based on the iteration. So I'm actually going to, instead of doing an attribute, what we're going to do is a variable. And the difference between a variable and an attribute in a wrangle context, like we are here, is that an attribute is something that's either being taken in or output. So we're going to actually see output here in our geometry spreadsheet. A variable is a number that is only being used and referenced here in the wrangle. It's never going to be seen or used outside of this particular wrangle context. And the reason we do that is primarily to save memory. It's always a good idea to reduce the number of attributes that you have on all of your geometry, just because it saves space and time and RAM on your computer. So just like we had to tell Houdini what type of attribute we have, if it's a float or an integer or a string, we need to tell Houdini what type of variable we have. We just do it a little bit differently. Whereas if we wanted to create this integer attribute, I at iter_num, we use the I at to determine that. What we're going to do is we're going to say int, and that is going to let Houdini know that we are creating an integer variable, and we're going to call this iter. And now you can see, if I go down here, we no longer have our iter_num attribute that I had before. Let's bring our noises back so we have everything all together. There we go. So I no longer have that iter_num, and I also don't have this iter anything. Like, this just isn't being output. It only exists here in this wrangle. And I can show you that that actually does exist. If I set I at iter_num equal to the iter variable, you can see that now it's back. And it's back and it behaves exactly like it did before, where piece 0 is iter_num 0, piece 1, all these piece 1 attributes are iter_num 1, etc. So it's there, it's just not being output. Cool. So what we're going to do is create a random number based on that integer number. So we're going to create another variable. We're going to call this one a float, and we're going to call this one randnum. And for this, we're going to use a rand function. So we're going to do rand, we're going to open and close parentheses. Now what the rand function wants is a seed value between those two parentheses, and we're going to use that iter variable as the seed value. So each time the loop runs, it's going to use the current iteration number as a random seed to generate a random number. Now this random function only generates random numbers between 0 and 1. So it's a float value between 0 and 1. And we can see that if we create f at random value, we set that equal to randnum, this randnum variable. Now we can see, if we look at our geometry spreadsheet, if we ignore these noises and we look specifically at name, let's say, so piece 0 has this random value here. These three, for piece 1, they all have the same random value. Likewise, here for these 4, for piece 2, they also have the same random value, all the way down, again, to piece 55 at the very bottom. Here we can see piece 55, same random value. Great. So we know that that is totally working. However, I don't really want a random number between 0 and 1. I want more like a random number between like 0 and 4. So what I need to do is take this value and let's say multiply it times 4. So essentially what it's going to do is it's going to give me a random number between 0 and 4 now. Cool. Let's look and see what that did. So I should have, yep, there we go. So I've got values. I've got 1.6, I've got 3.25, I've got all kinds of random numbers between 0 and 4 now. But I don't want them to be a float. I want nice clean integer values. So what I'm going to do is I'm going to create, instead of doing this float output, I'm going to create a integer attribute called subd. And I'm going to take the float variable here and I'm going to make it an integer by again using int, but in this case, I'm going to use parentheses and I'm going to put randnum inside those parentheses. So int actually gets used in a couple of different ways. You can create a integer variable by giving it this int type, or you can use int with parentheses here, and whatever is inside that is going to be processed as an integer attribute by Houdini. Okay, cool. So now what we have is we have our subd attribute randomized based on each little island, and it's generating a random number between 0 and 3, or essentially 4 random values. Now that we have that, we can actually take this and plug it back into our regular stream here. So I'm going to push the facet sop and the subdivision down. We're going to take the output of this for loop and we're going to plug it right back into our regular stream here. We're going to get things nicely aligned. And if you remember, the facet sop actually tells all the islands to be broken apart, so each polygon becomes its own island, and then the subdivision does exactly what it says it does. It subdivides everything. So what I want to do is set up a bunch of groups based on those random values to subdivide. What we're going to do is move the subdivide down. We're going to go up to the facet sop, and we're going to do a group expression sop. And that's going to allow us to essentially create a bunch of different groups based on a bunch of little tiny expressions. So we could do this in a wrangle as well, but I figured this way would be pretty easy. So we'll set up our first group. This will be subd0 is our group name. And we're going to set this up basically to say that any polygon that has a value of 0 for our subd gets put into the subd0 group. And then we're just going to do this a bunch of different times. So we'll do I at subd 2 equals and then 0. So essentially what this is saying in this very kind of truncated expression here is that if the polygon's subd value is equal to 0, put it into 0. The reason we do 2 equals is that this is essentially a shortened version of an if statement. And if you remember correctly, with the if statement, we need the double equals sign. Okay, so you can see we have a whole bunch of those polygons that just turned orange, and we see our subd0 group has 92 members in it, which is great. So I'm going to hit this little plus button and we're going to create another group. This one is going to be subd1. And we're going to say I at subd is equal to 1. And so we have a whole bunch of other polygons that just turned orange. We have 92 in subd0 and 135 in subd1. We're going to do this a couple more times. Group subd2. I at subd is equal to 2. And for our last one, of course, we'll do subd3 and I at subd is 3. Okay, so we have 92 here, we have 135 in subd1, we have 80 in subd2, and 108 in subd3, and all of that should add up to 415 polygons. Great. So now we just build out our various subdivide nodes. So this one, I'm going to take this back to a depth value of 1. And let's do this. Let's take this to a depth value of 0. This will be our subd0. I'm going to duplicate this, put it back in line. This one will be group sub D1. We're going to change the depth to a value of 1, so you can see already we have some polygons that have no subdivision and some polygons that have a subdivision of 1. So we're going to keep on going. We're going to put this down here. This one will be sub D2. We'll set this to a depth of 2. And you can see now we've got 0 and we've got 2. And we've got 1. So we've got a bunch in here. And let's do one more. Bring this in here. Set this to sub D3. And a depth of 3. Okay. It seems kind of silly to do a depth of 0, so let's actually just add 1 to all the depths. So sub D0 will be a depth of 1. Sub D1 will be a depth of 2. Sub D2 will be a depth of 3. And sub D3 will be a depth of 4. Just so we have more subdivisions. It doesn't make any sense to have a subdivision of 0. We might as well just not have it in there at all. Great. Cool, so now that we have all of those subdivided, our next step is to actually bring that detailed noise that I was talking about from Cinema 4D down here and transfer it onto all of our new subdivided polygons. So let's jump up here and we will grab this stuff. Whoops, grab this whole box. I'm just going to bring this over here. Now, this was stuff that we imported at the very, very beginning. This is our dense cube. And the dense cube actually has several different types of noise in it as well, which is really cool. And what I'm going to do is throw in an attribute transfer. And we're going to wire this up. I do want to see some of this noise. So in order to do that, I'm going to use a color sop. And I'm going to say, let's do primitive. And this is actually, these are all vertex attributes. So I need to promote them to being primitive attributes. So we're going to do attribute promote. And we are going to promote all the things from vertices to primitives. And instead of going through and putting in all of these individual names, I'm just going to put a star. Cool. So what the star does is say everything, all the things. So now everything that was previously a vertex attribute has been promoted to a polygon attribute or a primitive attribute. So I've got all of these attributes in here. Now, I don't actually need all of those attributes. I really just need the noises. I just didn't want to have to type out all that stuff. I don't really need UV and I don't really need normal. So I can actually write in an exception here. I can put this little caret and I can say N and caret UV. Cool. Okay, so you can see that N and UV have remained behind because I'm using this little caret to say except these attributes. And I've got the star saying everything. So it says everything except normal and except UV. So I've got this color sop and it's currently set to primitives and we've promoted all these attributes to primitives. But I kind of think I want to do what I had done before up here. If you remember way back over here, I had actually taken, after I had done all this, I had set all of these noise attributes to equal just one value of our vector attribute coming off of the noise, because noises, when they come in, are all 3 float vector values. I don't need all 3 floats. I just need 1 float from each one. So before the color, I'm going to throw in an attribute wrangle, and we're going to do a primitive. We're going to say, we're just going to set it up real simple again. We're going to say f at, we're going to start at noise 4 because our previous noises were 1 through 3. So we're going to start at noise 4. I'm going to set this one equal to v at ober1 dot x. We're going to say f at noise 5 is equal to v at ober1.y. Oh, I lied. ober2.x. There we go. That makes more sense. Great. So now I have too many attributes, right? I've got noise 5 and noise 4, and I still have the obers. So what I'm going to do is attribute delete. And for primitive attributes, let's see what primitive attributes we have. We have all of these things here. So I'm going to do sort of a similar thing to what I did before. I'm going to say delete all, whoops, delete all with the star, except noise 4, and except noise 5. Okay, so that should have removed everything except for noise 4 and noise 5, which is great. That's awesome. And so here in the color, I can say, let's do ramp from attribute noise 4. Cool, so there's my noise 4, and I also have noise 5, which is this one. So we're going to go with noise 5 for the moment, but let's, we may end up changing that. So I'm going to take the output from my attribute delete. I'm just going to skip over this color because it's really just there for visualization. I don't really need the attributes. I'm just going to bring those down here to attribute transfer. And for attribute transfer, we're going to turn off point attributes. I don't want to transfer point attributes. We're just going to transfer primitive attributes, which are just these two. So I don't have to do anything at this point. Let's throw in a color just so we can see those attributes having been transferred. So we'll do primitive attributes, ramp from attribute. We'll do noise 4, which is this one, and noise 5, which is this one. Great. So we're going to go with noise 5 for the moment, but we'll come back to that. So what we want to do is we want to create new polygons based on these noises. So we want to take our subdivided polygons, these guys here, and we want to use that noise to basically define the edges of new polygons now that we have all this detail and we've got this attribute that's been transferred. So the way we do that is using a divide sop. And the divide sop has this function called remove shared edges. So if I go up here, we go to our attribute transfer, we take this, plug it into the divide sop, and our divide sop, we can check here so you can see what the divide sop is doing is actually triangulating everything by default. If I click remove shared edges, it's actually going to remove all the edges. Now, everything looks kind of funny because I've got some normals that I don't need. So I'm going to do an attribute delete. Before we even get in here, we're just going to remove the normals off of the vertices. We don't need those. That's just screwing us up. But you can see essentially what it's done is it's taken us back to right where we began, which doesn't really do any good, right? So it's just removed all of those subdivisions, which is, I mean, that's handy, but it's not really what we want. So what I'm going to do is I'm going to set up two groups to basically define where that line of division is going to be, and we're going to do that based on these values here. So if we look at, we're using noise 5. So if we look at noise 5 values, just noise 5 values alone, our maximum is 0.97 and our minimum is 0. So we actually have a whole bunch of them that are at 0. So we've got a pretty good range of values here. So what I'm going to do is I'm going to create a group expression sop. We're going to throw that after our attribute delete. And we're going to say group 1 is going to be at noise 5 is greater than 0.5. And then we're going to throw in another group. We're going to say group 2 is equal to at noise 5 is less than or equal to 0.5. We account for all of it. So we've got, you can essentially see what we have here. These are more or less going to define our edges. Now, I'm going to go back in and tweak these numbers here in a minute, but I just want to show you what this is going to do. So we've got two groups. We've got group 1 and group 2, and those groups are essentially going to define where the edges of our new polygons are going to be. So if I go to my divide sop and I say, let's process this one as only group 1, you can see now we've got these kind of interesting little chunks, right? And likewise, I need to do another divide stop after this, and this one is going to process group 2. So what we have is these kind of shapes that cross over the boundaries of our square, which is really cool. Great. Now, I'm not entirely satisfied with the division of this just yet, because if we look here, group 1 only has 4,700 polygons in it, where group 2 has 30,000. So that's not quite right. I want to even that out a little bit. So I want to essentially decrease this number. Let's try 0.3 and 0.3. So now I'll have something that feels a little bit more even. I've got 15,000 and 19,000. That's a little better. And you can see the distribution of that is much nicer as well. Cool. Yeah, that's breaking things up fairly effectively. Now that we have them all broken up, let's go ahead and let's clean them up a little bit. So we'll throw in a clean SOP. Which is just going to help remove anything, any issues, fix any overlaps. We don't want to consolidate points, but that's all fine. Then let's give them some new normals. Give them some new point normals. We'll leave that alone. And then let's do a poly extrude and extrude these out a bit. So we want to do... we want to set these to individual elements, and we're going to extrude them out so you can see they're all extruding at the same distance, but of course we know we can change that, so we can go to local control, we can change the distance scale, we can change this from Z scale. Let's make this the noise 4 attribute. There we go. That's pretty cool. Let's extrude those out. Let's see what we got going on here. Yeah. That's fun. We've got some nice kind of breakup of all of those squares. So we've essentially turned all of these into like sort of Greebles, right? Which is pretty fun. A little bit more detail than we had in there before. And of course, we can go back in and change all of these values as much as we want. So we can add more or even less detail or whatever it is that we want to do.